Hey, everybody. This week, we're going to talk about confidence intervals. And personally, I'm excited because I think that when we start talking about confidence intervals, we really get to the beginning of what we can functionally do with data. From here on out, you're going to see a lot more hands on work rather than just thinking about abstract concepts related to numbers. So let's get started. A confidence interval is a range of numbers that we are certain that our population parameter, which would be the actual score in the population, falls within. So when we calculate the mean of a sample, the confidence interval around that mean is the range of values that we are certain the mean of the population would be. We're never 100% certain when we're talking about a sample because we know we have sampling error. We know that we have misrepresentation of our population within that sample. Several weeks ago, we looked at a data set that had computer-mediated immediate behaviors of professors associated with the amount of perceived immediacy their students had with those professors. We found that there was a correlation of negative 0.64, which meant that these relationships were moderately inversely related. The more of these behaviors that professors engaged in, the less cold they seemed. And vice versa, the fewer of these behaviors that they engaged in, the more cold they seemed. We said several weeks ago that this significance level right here was important, but we weren't really ready to talk about why yet. We also said that this was a p-value. A p-value is a probability value. It relates to the confidence interval. Right here, we know that we have a confidence interval of greater than 99% because this p-value is less than 0.001. We said that we wanted our p-value to always be less than 0.05 in order to be confident that we had a relationship and it wasn't just occurring by chance. And this is because we wanted to be 95% confident. In SPSS, instead of looking at the data with a p-value, we actually have the option to go to Analyze, Correlate, and bivariate with confidence intervals. Select computer-mediated immediate behaviors and perceived immediacy. Run it with a 95% confidence interval because we want to be 95% confident in our finding and hit OK. SPSS will calculate the confidence interval for us. You see that our correlation value is exactly the same. The way you read this confidence interval is to say that we're 95% certain that the exact score is negative 0.637, but we're 100% confident that the actual population parameter, the actual relationship we would see in the population falls between negative 0.696 and negative 0.568. The larger your sample size, the smaller your confidence interval will be because you have more data from which to better estimate that population parameter. Your textbook spends a great deal of time this week focusing on calculating the confidence intervals around means. It provides you with two separate formulas, one for the population and one for the sample. If you're calculating the confidence interval around the mean for the population, it means that you have enough prior data about the population that you're pretty confident that you can estimate the standard deviation of the entire population. Otherwise, if you have to calculate the standard deviation from within your sample, you're going to use a very different formula. For using the population confidence interval statistic, we use a z-distribution to decide what goes here. If we're using the sample, we use a t-distribution. Z-distribution just means normal distribution. If you recall a few weeks ago, we said that roughly 95% of your data falls between -2 and +2 standard deviations of the mean. That was a little bit of rough estimation. The real exact values are that 95% of your data falls within -1.96 and +1.96 standard deviations from the mean. So when we're using the formula associated with z-values, typically we're going to be using 1.96 because in business, we typically work with a 95% confidence interval. You don't have to use 95% though. Just because that's standard in business doesn't mean it's standard for everyone. There might be situations in which you are okay being less than 95% confident. If I'm picking a new flower arrangement for my backyard, I might be okay being 90% confident that the flowers I'm choosing are going to survive in my soil type before purchasing them. However, if I'm a surgeon and getting ready to try some new experimental treatment on my patient, I'm probably going to need to be more than 95% confident. I'll need to be 99 or better if possible. So the confidence interval you use depends on what you're working with. Now, if I didn't provide you with this little cheat sheet of a table, where would you go? You would go to your Z table. Remember before when we said that you look for the first two digits of your Z value here and the last digit here. These values represent percentages. Looking at our formula, we're looking for Z sub alpha divided by 2. Alpha represents the amount of uncertainty. We're looking for a Z value associated with alpha over 2. If alpha is 5%, then alpha over 2 is 2.5%. Therefore, we're looking for the Z value that goes with 97.5%. When you hunt for it, you find it right here, 0.975. And that Z value is 1.96. So that's where you would get that 1.96 or any other Z value to go in such a calculation just from the Z table in the back of your book. What if you need to use a T value because you're calculating a standard deviation from within your sample? T values come from T distributions. It's a slightly more peaked distribution than your normal distribution curve. T distributions help us to account for a little bit more of that sampling error when we're not totally confident in our representativeness to the population. You can also find T tables in the back of your book. We'll learn more about the tails of the T's later on. You see here where it says one tail versus two tail? Here you can look at cumulative probability to understand what's happening. Here we have a T in which we want to be 0.975% confident. Which T value we use depends on the number of degrees of freedom we have in a sample. Degrees of freedom, as you'll read more about in your textbook, are essentially options for getting to that last output. You look up the T value you need by looking at the cumulative probability and the degrees of freedom you have. Let's look at an example in Excel. Here's a table showing student exam scores from a class. Let's look at the descriptive statistics. I'll give it this range. And notice here, our default is that we've always been using a 95% confidence level for the mean. You can change this confidence interval to whatever you want, but 95% is standard in business. Let's start putting my output here. And what do we have? We have a mean of 77.6666 continuing and a confidence level of 8.35. Well, what does this mean? It means that for the population, the average exam score falls within 8.36 plus or minus this mean. So that means our lower bound equals the mean minus this confidence interval, and our upper bound equals the mean plus this confidence level. So we're 95% sure that the average score on this exam for the population of all students who have ever taken it falls between roughly 69% and 86%. How do we know whether Excel is using a z-score or a t-score for this calculating, though? Well, actually, Excel has to be using the sample formula because we didn't give it a standard deviation for the entire population. This means that Excel had to calculate its own standard deviation and calculated this confidence interval based on the sample standard deviation that it computed for itself. The other thing your textbook talks about this week is estimating sample size. Given a known standard deviation estimated for a population and the amount of error that you're willing to accept, what is the sample size that you would need to have ample statistical power to find a mean with 95% confidence? Forgive my terrible handwriting. But let's say, for example, that you wanted to know how large your sample would need to be 95% confident with a standard deviation of 20 units and an error level of 2, that what you found wasn't by chance. And because we want to be 95% confident, we use z equals 1.96. We square our z values. We insert the standard deviation that we are assuming. We square it, so 20 squared. And then we divide that by the error amount. Here, we said it would be 4 squared. So 1.96 squared times 20 squared divided by 2 squared is 384.16. When you're doing these sample calculations, you always round to the nearest whole number because you can't have a partial sample unit. So in this case, we would need a sample of at least 385. So there's your crash course in confidence intervals. I encourage you to spend some time this week thinking about how confident you need to be in various parts of your life. When are times that you can be only 80% confident to move forward with a decision? When do you feel like you need to be 99% confident? Becoming aware of your own confidence levels is going to help you appreciate statistics more when you encounter them outside of this class. If you have any questions, let me know.